Good morning or good afternoon, depending on where you are at. Bring to you webinar. The title is a comprehensive formulation prioritizing bridge intervention subject to flood hazards. We are delighted to have with us Dr. Eren Özguven, who is an associate professor at FAMU FSU College of Engineering in Tallahassee. Eric Barima, who is a PhD candidate at FAMU FSU College of Engineering, and Nitesh Sharma, assistant professor at FMU FSU College of Engineering. During the registration process, we have received a number of questions. The question and answer period is going to be moderated by Paul Lyles, formerly with the Georgia Department of Transportation, and also Don Degerman, who is also with the Georgia Department of Transportation. At this point, before we start our webinar, we have some news that we would like, very important news, in fact, that we would like to share with you related to 2026 conference that is right around the corner. I also wanted to take this opportunity to introduce our new faculty who have joined Florida International University. She's an assistant professor, Dr. Julia Marasco, who come with us from the Lehigh University. Dr. Marasco is also co-director of our center, IBT/ABC/UTC. At this point, I'm going to ask Dr. Marasco to share some news that she has with respect to the 2026 World Bridge Engineering Conference.
Atorot, for your kind introduction. I'm really glad to share more information about the 2026 World Bridge Engineering Conference. The conference will be on December 1st and 2nd in Miami at the Regency Hotel. It is sponsored by the US DOT, and we would like to thank also the co-sponsor state DOT. We receive a tremendous amount of abstract, but the deadline to submit them has been extended to May 25th. So you can proceed with the submission online or on our website or using the QR code. As regards the registration is open, therefore please proceed with the registration on the website or using the shared QR code, and we recommend registering at your early convenience. There is also a travel scholarship program for bridge owners in US. The deadline to apply is May 25th, and you can find all the information on our website. Very important, in conjunction with the conference, this is also an award program. We are going to give awards at different categories, so please visit our website, see the different categories where award we will be given, and proceed to submit your nomination. And finally, I want also to underline that the day before the conference, I'm organizing a workshop on non-destructive testing techniques. This is a workshop where a lot of companies are involved. During the morning, there will be a lot of presentation. Instead, during the afternoon, we will have hands-on experience. So for more information, please contact me. And I want also to underline that this workshop is free for who will be attend the conference. And please just send me an email. I will be happy to answer and provide all the information. So at this point, I'm going to turn it to Atorot.
Thank you, Julia. So our next monthly webinar is going to be held on Thursday, May 21st. The title of the monthly webinar for May of the 2026 is In Response to Fern Hollow Collapse, City of Pittsburgh Overhauls Bridge Asset Management. Today, again, we are delighted to bring to you a very interesting presentation, a comprehensive formulation prioritizing the bridge intervention subject to the flood hazard. Our speakers, Eren Özguven, Eric Barima, and Nitesh Sharma. With that, I'll turn the screen to Barima, Nitesh, and Eren.
Thanks a lot, Atorot. I appreciate the kind introduction. Good afternoon and good morning, everyone, again, wherever you are. My name is Eren Özguven. Thank you so much for joining our IBT/ABC/UTC online research seminar today. We are going to show the findings of a research project going on at the Florida A&M University, Florida State University College of Engineering today, funded by our UTC. Now, our presentation title is A Comprehensive Formulation Prioritizing Bridge Interventions Subject to Flood Hazard. But first, I wanted to give you a brief background of our research activities here. We are a multidisciplinary research group at the FAMU FSU College of Engineering, focusing on a variety of areas with a potential to help our center including water sustainability and coastal hazards, resilient materials and structures, operations research and transportation resilience applications, and sustainable infrastructure management. We have 16 in-house faculty with more than 60 graduate students, and we do have track ties to many cities, communities, and nonprofits as part of our projects. Our research team for the UTC projects we currently have includes me and then 2 assistant professors, 2 junior faculty, Chanwen Vivian Guo and Nitesh Sharma, and 2 experienced senior faculty, Professors Ram Moses and John Sabanjo. We also have in our group 1 postdoctoral research associate, Vishnu, and 3 graduate students, Eric, Onindo, and Mansur, working on our projects. Now, I would like to leave the floor to Dr. Sharma, where we will present our findings from our project titled Intellivis Comprehensive Human-Centered Risk-Based Online Platform for Evaluation, Visualization, and Prioritization of bridge projects. Nitesh, floor is yours.
Thank you, Aaron, and thank you everyone for joining. To give you a brief introduction to this project, Eric has been working with me, Aaron, and also with contributions from our other graduate students and postdocs in several projects under the UTC. One of the things that we've been trying to work on is how to prioritize bridges so that we can have them maintained at good structural health, also managing economics of the investments at different times into the assets, as well as reducing the overall vulnerability to natural hazards, in this specific case, floods. So here we are trying to incorporate structural health indices, net present value of money for investment, as well as doing some structural fragility analysis for bridges. But with all of that, we are also trying to assess the overall functionality of the bridges with respect to the transportation network, so that basic necessities and emergency services could be provided with a higher level of reliability to a community where these assets are situated. And with that, Eric, the floor is to you.
Thank you, sir. Hello, everyone. My name is Eric Chumberima. I'm a PhD researcher at the FAMU FSC College of Engineering, and it is an honor to stand in to present our research titled A Comprehensive Formulation Prioritizing Bridge Intervention Subject to Flood Hazard. This research was supervised by my research advisors, Dr. Erin Osgovin and then Dr. Nitesh Sharma. By the end of this presentation, we aim to demonstrate a structured and data-driven approach for prioritizing and managing transportation infrastructure. Today's research is going to follow this format. We are first going to talk about the background, and then we also talk about the literature review we did on this topic. We're also going to talk about the study area, and then we'll spend some time here at the methodology section. After that, we talk about the results, and then Dr. Nitesh Sharma will again come back to talk about the research dissemination. Across the world, and even in the United States here, we are seeing an increasing reports of destructive flood events. These floods are not just subject to environmental issues, they directly impact transportation systems, especially bridges. To add to that, bridges in the United States are aging. This points to the fact that there's a need for maintaining bridges across the country. However, to construct or to repair a bridge is very expensive, and especially with a limited budget for bridge repair, this becomes a challenge. So the question we ask ourselves is, how do we prioritize bridges with the limited funds we have, the limited funds or budget we have? So to do that, we did some literature review on this topic, and then among our literature review, we were able to review them into 4 main themes. Each theme contributes important insights, but also reveal a key gap that motivates this research. The first theme we focus on is on bridge structural health assessments. The studies such as Intosio et al. Have explored advanced methods for detecting damages and for detecting bridge damages. Other research in this team also talks about the nonlinear bridge health index in this field. For instance, Jen and Brent's research, as well as Inkum et al. Examine how both linear and nonlinear approaches of computing bridge health index affects the sufficiency rating used by the Federal Highway Authority. However, these studies primarily focus on the physical condition of the bridges, with limited consideration on how the conditions affect the broader transportation network. The second theme we also examined were the impact of infrastructure on accessibility and interdependencies. Pioneer researcher like Rinaldi et al. Did Nadia Eta introduced the concept of cascading failure in interconnectedness systems. Similarly, Sharma Eta also provided a unified framework for modeling infrastructure interdependencies. Also, Mustafavi also provided a unified framework for modeling, an extended resilience, incorporating stakeholder decision-making and resource allocation. Despite these contributions, most of the work remained conceptual with limited integration of detailed asset-level bridge conditions. The third theme we also considered was the socioeconomic impact on bridges. Studies such as Donovan and Brooks highlight the role of bridge in supporting rural economies. Paul Gandhi et al. Also showed that disadvantaged communities are disproportionately affected by bridge deterioration. Martins also emphasized that accessibility rather than mobility should be the central aim in transportation planning. This research also had a limitation on linking the bridge conditions and disruptions to the population level impact and accessibility outcomes. Finally, the last thing we considered was the bridge prioritization. Recent research from Sopanjo and Thompson emphasized the importance of incorporating risks and vulnerability into the prioritization framework. Earlier work by Gokey also integrates structural economics and policy consideration. Whilst this research were really good, and then we also adopted some in our research, most of them were engineering focused with limited incorporation of spatial accessibility and how it affects the society. Overall, the literature shows a strong advancement in individual areas. However, there's a clear gap in integrating these dimensions into a unified data-driven framework. So this led to our research aim, which was to develop a comprehensive data-driven bridge prioritization framework that supports optimal decision-making under constrained funding conditions. Duval County was selected as a study area because it provides an ideal environment to demonstrate the scalability of this proposed framework. Duval County includes a mix of urban, suburban, and mixed and rural area. Duval County also has a large complex transportation network and a diverse population distribution, meaning the model, when tested here, will provide a realistic and heterogeneous condition to scale it to other parts of the state. Because of this combination, the framework was developed here and then so that it can be extended to other parts of the. Duval County is also a coastal region which is exposed to flooding. So this makes it a very highly relevant case for our resilience analysis. So here we get to the methodology section of our research. At the core of this research, a composite prioritization model which integrates multiple dimensions of bridges performance in a single decision making. So our model is to provide a composite prioritization model for decision making on how to prioritize bridges as a transportation infrastructure. So rather than relying on a single metric like condition rating, the model combines 4 key components that collectively define how critical a bridge is. First, you consider the structural condition, which represents physical state of a bridge. Second, we also incorporate the bridge fragility, which represents the probability of failure under flood scenarios. And third, we evaluate accessibility impact, which measures how the failure of a bridge affects travel time to critical services. And finally, we include economic impact, which accounts for the cost implications of repair, replacement, and delayed interventions. These 4 components are integrated into a unified framework to capture structural vulnerability, hazard exposure, functional impact, and economic consequence in a single model. In the following sections, I'll walk you through each of the components and how they are quantified and incorporated in the prioritization process. For the structural assessment, which is the first component you are going to consider, we use data from the National Bridge Inventory, which provides standardized condition rating for bridges across the United States. From the data set, we extract key components from the bridge, such as the structure ID, deck condition, the superstructure condition, the substructure condition, and also the culvert condition. From the Federal Highway Authority, the bridges are classified into 3 components. The first component is the deck component. Here, the deck carries the traffic loads and represents the user interface of the bridge. Below the deck is the superstructure. The superstructure includes elements such as the girders and then the beams that support the deck and transfer load downwards. For the substructure, consists of the piers, the abutments, and foundation, which transfer loads from the bridge to the ground. From the National Bridge Inventory, to quantify the structural condition, the National Bridge Inventory uses a condition rating, which starts from 0 to 9. 0 being that the bridge is in a failed condition, and 9 means the bridge is in an excellent condition. This classification simplifies the interpretation and allows us to consistently identify bridges that may require maintenance, rehabilitation, and prioritization. However, the National Bridge Inventory provides these ratings. They are ordinal and may not be directly suitable for the quantitative analysis we do. So to address this, we develop a transformation creates a continuous structural condition from 0 to 100. The figure here shows the transformation functions. The linear relationship assumes a uniform distribution. The nonlinear allows us to better capture the fact that iteration accelerates at a lower condition state. In this research, we adapted a nonlinear transformation with a nonlinearity of 1.75, which reflects a more conservative and pessimistic assessment of structural conditions as progress deteriorates. So after creating the condition rating, we created a bridge health index, which we were able to use to rate the bridges in the Duval County as per their bridge structural health. And so this is a spatial display of the bridges in Duval County per their structural health. The red here shows bridges that are poor states, and the green shows bridges that are in excellent state conditions. So after doing the structural health, we went on to model the flood fragility. This is an important component in the prioritization framework because it estimates the bridge fragility, which quantifies the probability of failure under flood conditions. This is particularly critical because not all bridges are equally exposed to flood risk. Bridges that are located within waterways are directly subjected to hydraulic forces such as drag, lift, and score, making the bridges significantly vulnerable. In contrast, grade separated bridges are typically elevated above flood levels, and so they experience minimal hydraulic interactions. So by modeling this fragility, we are able to distinguish between these types of bridges and identify those that are truly at risk due to flooding, thereby ensuring that we are prioritizing bridges that are most vulnerable to hazard of focus. So here we use data from the NBI and hazards for the bridge classification. We also got flood return period from the FEMA map. And we also got bridge geometry data from LiDAR and NBI as well. And finally, we also got discharge data from the US Geographical Survey. So for our fragility framework, we first did bridge classification based on the structural and geometric characteristics. These steps allow us to assign necessary parameters for modeling of the flood. Next, we went to flood modeling. This is where we perform modeling to estimate the hydraulic demands at each bridge, including the flow, the depth, and the velocity. Third, we did a reliability analysis at the component level, evaluating how the bridge deck, the pier, and the foundation respond to the applied load using defined limit states functions. And finally, we use a probabilistic simulation to estimate the probability of failure for each bridge and accounting for the uncertainty in both loading and resistance. First, we're going to talk about the bridge classification. Here, we group the bridges into 15 representative classes based on their key structural attributes. We focus on the bridge, the span system, the type of material, the pier type, and then the support conditions. Specifically, we wanted to find out whether the bridge is a single span or a multi-span. We also wanted to find out whether the material used were concrete or steel. We also wanted to find out whether the pier type was a single column or a multi-column vent. And finally, we also wanted to see if the support condition was a simple support or a continuous support. All this classification was informed by the hazards methodology, which was adapted to our available NBI data. So after doing the classification, we went ahead with the flood modeling step, which involved the estimation of the hydraulic conditions at each of the bridge locations. Here, flood depth was obtained from the FEMA map based on a 100-year return period. The 100-year return period corresponds to a flood with a 1% annual probability of occurrence. This also provides a consistent benchmark for evaluating bridge vulnerability. So when we get the flood depth here, we want to get the flow velocity, because in our flood modeling, we are looking for two intensity measures, which is the flood depth and then the flood velocity. So when we get the flood depth from the FEMA map, we also move ahead to get the flood velocity. So for the flood velocity, we are interested in two quantities, which is the discharge at the bridge and then the cross-sectional area of the bridge. The discharge at the bridge is computed from this relation. In this figure shown here from the US Geological Survey, we can see that there are stream gauges all around the nation. These stream gauges provide observed discharge data, which are used for the computation of the quantity of flow under the bridge. So with that, we are able to get the flow velocity of the bridge passing at the bridge, and from there we can use the values there to do our reliability analysis, where we consider the individual components of the bridge. So here, for start, we are going to start with the bridge deck. So for a bridge deck to fail, either two of these failure events have to happen. Either there is a transverse failure or an uplift failure. For an uplift failure to occur, the uplift force of the river acting on the deck should be greater than the self-weight of the bridge. And at the same time, the drag force acting on the bridge deck should be greater than the resistance given by the bridge. When these two events occur simultaneously, that's where we experience an uplift of the bridge deck. Similarly, for a transverse failure to occur, these two events also have to occur simultaneously. First, the drag force acting on the bridge should exceed the frictional resistance of the bridge deck. And at the same time, the uplift force, and in this case, the uplift force acting on the bridge deck should be less than or equal to the self-weight. Another way to say this is that the bridge deck must be in contact with the support during the time that the uplift, the drag force is acting on the bridge, so that for the transverse event to occur, the transverse failure event to occur. The transverse failure event is the sliding off of the bridge deck by the force of the water. And so when these two events occur, which is the uplift force and the transverse force occur, then the bridge deck is considered to have failed. The second component you are going to consider here is the pier failure. For a pier failure to occur, the longitudinal moment and the transverse moment acting on the pier should be greater than the capacity of the pier. When this event happens, it may cause the bridge pier to crumble and then fail, which may bring down the whole bridge. Finally, the last failure of the bridge we are going to talk about is the foundation failure. So for the foundation to fail, either of these three failure events have to occur. The first event is when the vertical load of the bridge is greater than the vertical compressive resistance of the soil. When the lateral load of the bridge is greater than the lateral load resistance of the soil. When the combined effect of the axial load and the bending moment exceeds the foundational structural capacity of the foundation, that's when the foundation of the bridge is considered to have failed. These failures are explicitly modeled in our limit state equations and in our probabilistic simulation in order to get the results. So the slide here represents the resulting bridge fragility estimate, showing that the probability of failure across the network are modeled for the various scenarios of the bridges. So the figure we see here shows the spatial distribution of bridge failure across the study area. And then this figure shows the fragility surface that illustrates the probability of failure, which increases with increasing water depth and increasing velocity. Third component of the composite prioritization model is the accessibility impact of the bridges. Here, accessibility is here we consider accessibility to be accessibility in this context refers to how easily people can reach essential services through the road network. We model using the network-based approach where sensor structure represents the demand and then represent destination. Beyond accessibility, we are also interested in understanding how important the bridge is. So this concept within network, we call it the degree of centrality. In simple terms, degree of centrality measures how connected a node is within a network. So for our bridge scenario, this reflects how many roads are connected to the bridge. A bridge with a higher centrality acts as a critical connector, meaning more paths in the network are connected to the bridge. This makes the bridge very relevant to the network. Also, so for this work, we collected demographic data from the census tract level. We also collected census coverage data using considering the hospitals, fire stations, police stations, and grocery stores. And we also use transportation network from the OpenStreetMap. So for accessibility framework, we begin with the origins. Here we selected origins from the census tract, which represents the population weighted centroids. These capture where people are located in the county. We define destinations, which are essential services such as the hospitals, the fire stations, the police stations, and the groceries. These services are most needed in times of emergency. And then using the transportation network, we compute a baseline where travel time from each origin to the nearest services are computed using the shortest path approach. We create a disruption scenario. To simulate the disruption, we remove one bridge at a time from the network and recompute the travel time. With that, we get an accessibility loss, which is different between the disruption time and then the baseline time. We're able to create an accessibility impact, which helps us to find which of these bridges are very important to the network. So as you can see here, the figure here shows the distribution of bridges in Duval County that have high importance to the network. And one of these bridges is the John T. Assau Bridge. Building on the previous slides, we also talk about how important these particular bridges are to the services we are talking about. So for instance, here we're still talking about the John T. Assau Bridge. which when disrupted, when the simulation is disrupted, or when that bridge is removed, how it affects the population in terms of access to police station. So in other words, when this bridge is broken and then the police needs to access this area, there was a massive, which implies, which is very critical, because in times of this emergency, every second counts for the population here. Another example is when, for this population, in terms of accessibility to hospital. So we realized that when this bridge is broken, this whole population was affected in terms of hospital, especially considering where the spatial distribution of the hospitals. Finally, here we also expanded on an analysis to include all the essential services, which is again the grocery stores, the hospitals, the fire station, and the police stations. Each map here shows the accessibility loss variation depending on the type of services. So, for instance, for the grocery stores here, the grocery store shows accessibility loss, especially in the peripheral regions of the county. For hospitals, the accessibility loss appears to be also kind of central in the county. And for fire station and in the police station, services show different spatial sensitivity depending on the network and the location of the services. To better understand who is impacted by these accessibility laws, we classify the study area into settlement types, which are the urban, the rural, and then the suburban or the mixed settlement types. Comparing back to the previous slide, we could see that most of the accessibility laws were found in the peripheral regions or the rural side of the county. You can see that for urban areas, there were moderate impact, which was mainly due to the redundancy of the network. However, for the rural side, they experience significant impacts in terms of accessibility loss. This is also mainly due to the lack of alternative routes in the rural areas, which is consistent with what we learned from literature that when the bridge breaks, it will mostly affect the rural communities, and disadvantaged communities are impacted most in times of when a bridge is broken. So this brings us to our last component of the prioritization model. With this economic analysis is built on 3 key data components derived from the National Bridge Inventory. We use a 20-year inspection record from 2005 to 2025, which provide a longitudinal data of the bridge conditions over time. Second, we use the superstructural condition to construct a structural condition index. And third, we use traffic data, specifically the average daily truck traffic, which captures the loading effects that contributes to the structural deterioration of the bridges. Also here, we frame that the replacement cost is equal to the construction cost by the demolition cost. In other words, in order to replace a bridge, you have to demolish the bridge and reconstruct the bridge. And so these figures were we got to estimate the replacement cost. We use estimates from the Federal Highway Administration, where we got the unit cost of construction and unit cost of demolition, which we multiply by the area of the bridge deck to get the estimate of the bridge. So to begin with our economic framework, what we first did was that computed the current superstructure condition of each bridge, which we derived from inspection data of the MBI data. So here we use the superstructure condition to compute current condition of the bridge. From there, we evaluate whether the bridge has exceeded the threshold we gave it. Here we give a threshold of 25. 25 here roughly corresponds to about 4 on the National Bridge Inventory Condition Rating, which is considered to be in a poor state. So here, if our threshold is exceeded, the bridge is considered to need immediate attention. And so here, that bridge moves into our immediate attention group. However, if the bridge has not yet exceeded the threshold, we estimated the time to failure. In other words, how long is the bridge going to take to fail? This helps us to estimate the time of failure, and so for which we can make an informed decision and decide whether to work on the bridge now or later. So to find the time to failure, we have to find the deterioration rate. To find the deterioration rate, we needed to create a deterioration model. So here we chose a panel regression in our deterioration model due to the evolution of bridge data over the 20-year period. From this model, we obtained an effective deterioration rate, which reflects the change or the deterioration of the bridge over time. So this deterioration computes for the time to failure. The estimates help us to rate the time to which the bridge is going to take to deteriorate. Next, we estimate the replacement cost based on the bridge characteristics. For this stage, if a bridge is to be replaced immediately, the present value of the cost is simply the current replacement cost. However, if the replacement cost is delayed, the cost changes over time due to 2 competing effects. The first effect is the construction escalation, and then the second effect is the discount rate. So from there, we do a ranking. During this ranking, we use the cost estimates to rank the bridges based on the economic impact of the delaying replacement. So here, the bridge is ranked into two economic indicators, which is the absolute penalty and then the relative efficiency of the bridge replacement. Since we have these events, we have now do the ranking based on a multi-objective framework by first maximizing the absolute cost replacement, the absolute cost penalty, and then second, we try to minimize the ratio of immediate to future costs using the Pareto front. From this ranking, we're able to calculate the economic priority index. The next question we ask is the index of the bridge high enough? So if the index of the bridge is high enough, the bridge then goes into the immediate framework. And then if the bridge is quite low, then the bridge is deferred for some time. So this helps us to arrange the bridges in terms of their priority, the economic priority. And so this is a spatial distribution of the bridges in the Duval County. So we have some bridges that exceeded the economic threshold. So that means they need immediate replacement. And then some of the bridges were ranked in the high priority. That means that those bridges, it was economically prudent to fix the bridges now than wait until later. So with that, we're able to come to a composite prioritization model. So the composite prioritization model, what we did was that we fused all the indexes we generated from all the four components into this prioritization model. So by now, we have our structural health index, and then we also have our bridge fragility or the probability of failure of each of the bridges. And then we also have the accessibility impact index, which helps us to know the importance of the bridge at each location. And then finally, now we have our economic priority index, which helps us to choose a trade-off of whether to fix the bridge now or we can delay the bridge later. So here is the composite prioritization framework. So here they have three main steps. The first step is the data integration, which we just talked about. So here we are able to fuse all the components into one component. And to do that, we have to standardize the variables because all these four components were in different metrics. So to use the data, we have to standardize them into one complete standard. And then the next stage we did was to do feature engineering. This is where we use the principal component analysis. The principal component analysis helped us to reduce the dimensionality. From there to be able to uncover the dominant pattern of the relationship among the multiple competing bridge prioritization indicators. And finally, the PCA also helped us as an early stage in our machine learning flow, since this research is going to evolve into a machine learning process where we can be able to predict the prioritization of a bridge at any particular time. And finally, we did the bridge prioritization using the Pareto analysis. So in this section, we applied the principal component analysis to understand the underlying structure of the four components of our prioritization model. On the right side here is a script plot, which shows how much variance each component explains. We see here that the first component explains about 38% of the variance in the data. The second component here explains about 26% of the variation of the data. And then the third component here explains about 23% components variation in the data. This table here also interprets what each principal component represents. And so for here, we could see that for the principal component one, the top driver was the economic impact, followed by the bridge health index. Whereas the principal component two, the top driver here is the accessibility impact and the fragility impact. Overall, the analysis tells us that the prioritization framework is dominated not by a single factor. Instead, it reflects a multidimensional structure where economic, structural, and accessibility considerations play a significant role. Next, we did a Pareto analysis. After identifying the key dimensions of the system using the principal component analysis, we then applied a Pareto-based multi-objective optimization to identify bridges that represent the most critical trade-off across the competing objectives. So here, this first plot here tells us the trade-off between the structural risks and the economic impact of the bridge. The red dot here represent the bridges that cannot reduce structure. So that represents bridges that when we reduce the structural risk cannot reduce the structural risk without increasing the economic loss. And so this presents a trade-off between the structural risk and economic risk. Similarly, Pareto frontier, it also shows us the trade-off between the structural risk and accessibility risk. It highlights bridges that are simultaneously critical in terms of failure risk as well as the network disruption. The radial chart here, which shows the top 5 bridges that to be prioritized in the county. Each axis here shows the key dimensions of the bridges, being the economic priority, accessibility, the fragility, and then the bridge health index. Here we can see that some bridges have high probability in failure, but may also have moderate economic impact. This clearly demonstrates the fact that bridge prioritization inherently is a multidimensional problem, not a single metric that captures the full picture. So ultimately, this approach ensures that we are not just prioritizing the worst condition of bridges, but those that pose a great risk overall in the system in terms of safety, accessibility, and economic impact. So this also gives us a spatial distribution of the bridges to prioritize in the Duval County. The bridges were grouped into tiers. We have the tier 1, which is the higher priority bridge to fix, and we also have the second priority bridge to fix, which is the tier 2, and we have the third priority bridges to fix, which is the tier 3. So for discussion, we learned that bridge priority is driven by a multiple interacting factors, not just one structural condition. Also, from our research, we also show that some bridges may be moderate, but also at the same time can be critical due to the risk it faces, the accessibility impact, or how important the bridge is to the network, and how economically critical the bridges. So some bridges are very economically expensive to delay maintenance or replacement. And finally, this research also provides a framework that enables data-driven, system-level prioritization for resilience decision-making. And so from here, Dr. Sharma continues with the IntelliVis web-based GIS dashboard that we are developing, a continuation of this project.
Thank you, Eric. So Eric so far covered all the conceptual and theoretical contributions that we made in developing this framework, but we have been constantly reminded by the UTC leadership that one of the main priorities of this transportation center is that we need to have impact into the practical application and use of the research that is developed by the center. So in that regard, what we are currently also working on for the past year is an online web-based dashboard that actually houses all of the work that we've been doing, and we'll try to share this publicly so people can use the research that we have done. And in this regard, we have made a lot of progress. So this platform has several components. So we have a web-based GIS dashboard. We also have a spatial database that includes all of the data sets that we have used. And then we also have the rendering system that can help you look at the findings from our analysis, as well as do your analysis for any scenario-based things that you would like to do with the data we have. So for the user workflow, there are two types of user workflows that we are expecting in the system, or we're trying to implement. One is that the user can look at a layer of data and just try to browse the information we have, or look at the results of our analysis, for example, this one for prioritizing bridges, or they can click on one of the analysis tabs that we have, and they can run these analyses and generate reports they can use for their research or for other purposes. Overall, we are currently working to improve this performance. At this stage, we are testing it internally within the university and the center, and we are trying to also incorporate other data as well as other natural hazards, because North Florida is also vulnerable to hurricanes as well as wildfires. So our overall plan is to have multiple natural hazards supported by the platform. So these type of analysis can be done for all of those things. Thank you so much for listening. And yeah, if you have any questions, we are here to answer.
Thanks for a very interesting presentation. I also wanted, before I turn it to Paul Lyles and Don Digamon for question and answering period, I wanted to add a word that to our audience, that this is a research seminar at IBT, ABCUTC. We have several technology transfer activity. One of our technology transfer activity is the quarterly research basically seminar. And the objective of the quarterly research seminar is to provide an opportunity for our graduate students to give a presentation alongside with their faculty advisors. The project that you just saw is one of the projects that has been supported by our center, IBT/ABCUTC, and the work was conducted at one of our partner universities. So we are 7 consortium university, FIU is a lead, and we have 6 partner university. FAMU/FSU College of Engineering is one of our partner universities. So at this point, I'm going to turn it to Paul so you can moderate the question and answer period.
Okay, Torrid, thank you. And everyone, it's real interesting on your research and what you have going on, trying to get all the data together where you can make some decisions. And we do have a few questions that came in. The first one here is there an Excel-based modeling system available for this?
Yeah, okay, so this model, we are now developing it, and then the next phase is to develop the dashboard. And so currently there's not an Excel model for it, but then we are developing it into a web page where we can make decisions on how to prioritize the bridges.
Okay, and does that mean it's really not available to the public to use yet? Is that correct?
Yeah, not yet, but we are working on it.
You have any timeline ideas on when it would be available?
Right, so I can answer that. So because these data sets are too massive and they also have a lot of geographic data, so the use of Excel in those type of things is not that practical, and it's actually hard to do. So we are currently using SQL and Python, but we'll provide a GUI, like a graphical user interface, so you can click and run these analysis without doing any coding on our dashboard. About the timelines, we are currently testing them, and we'll try to at least get our code out by the end of the summer. That's the current time.
Okay, that's good. Second question here was involving flooding, I guess. It says, could you discuss predicting bridge size needs based on bank full width versus hydraulic area available?
This question relates to bridge design. That's not something that we're trying to address. We look at the current inventory, and so we are just trying to use the models that have either been published by FEMA or USGS, and just try to assess the fragility of the bridges for the current or the predicted depth of flood and flood discharge through that bridge. So I wouldn't be able to comment on the design process for that. Thank you.
Okay. Along the same lines, there's a question that came in about, does it look at scour susceptibility at all in fitting with the model? That gets into the soils and everything else. Is that really not quite within the range of what y'all were looking at?
Right. So the scour of the foundation, it reduces both the axial and the moment load carrying capacity of the foundations. So the thing that Eric presented, it is an input variable to those. We are not developing any new models for predicting scour, but we are using currently available models to predict the current axial as well as moment carrying capacity of the foundation. So that part is included in the fragility of the foundation components to the flooding.
Okay, long involved question here. It said, can this be used in, I don't know if you're really looking at the type of bridge, but could this be used in all concrete construction versus maybe steel? Y'all don't really look at that, differentiate, do you?
We do have a classification for different types of concrete and steel bridges. So far, what we've developed is that we are limiting certain support conditions where the flood risk is relevant. So most of the time, simply supported spans that are not restrained, and some of them are present in the current region that we are looking at, and those have higher vulnerability to sort of uplift failures or transverse failures of the deck. So those become the first type of classes that we are looking at. But bridge classes are very diverse. So in that case, we are definitely not covering all of the relevant classes, but we are trying to at least look at the ones which are the most common, as well as the ones that are typically located in the rural parts, which are smaller bridges and usually single span simply supported sort of thing. So we are covering those.
Okay. Do you look at the difference in cost of the type of bridges at all?
Yes, like Eric mentioned, we are using the federal highway data and their cost estimation methods to look at different type of unit costs for different sort of.
Okay. Does it cover the different strength categories of the bridges?
Right. So currently we are limited by what we can find on the openly available data, but we are also working with some partners from the DOT side, and we are getting feedback on our formulation. So in future, if we are given access to more high resolution data or more structural data for specific bridges, this can be improved.
Okay, and the last part of this question was, what memory aid would you recommend to someone deciding if a bridge should be closed?
I think existence of a dashboard like this, where you are, where you have all the data, it's going to constantly remind you, because it's not like someone is remembering it. Anytime you open it, you can have a workflow that will warn you about which are the current bridges that need to be taken care of. Thank you.
Okay, I had a couple other questions here. One of them was in your accessibility data, and you went through a whole lot of stuff about getting census and this, that, and the other. But did you just use the ADT? That's the average daily traffic. You talked about using the truck traffic and another thing, but did you just use the ADT?
Right. So we are using those as well, but we are trying to do something which is not just about the ADT, which is access to emergency services. So those traffic may not be the high volume, but it sort of becomes an important component of the traffic, especially under emergency conditions. So we are including, we use the normal ADT for the mobility, general mobility accessibility, but we are also doing our own analysis for origin destination and network analysis for looking at the accessibility to essential services, food, etc.
Okay. In your service coverage, and you talked about hospitals, police stations, fire stations, grocery stores. Did you consider schools at all? And you know, sometimes that gets important for school bus routes. Just was curious.
Yeah, so I think because this one currently was focused on post-disaster, most of the schools actually serve as emergency centers as well, or shelters. We may not have presented it as part of this, but in one of the slides that is part of our online dashboard, we do have school locations. So that is part of our analysis.
Okay, got another question here. This one's pretty long. It's really broken into three parts. Did you use finite element simulations to generate the fragility surfaces? You said you really weren't looking at the structural part of it too much, so I was curious on that.
We did not use FEM. That's because the data requirements are super high. So this type of methodology is meant for doing a regional level sort of prioritization, and FEM workflow would be limited just because we don't have information on the bridges at that level. So there are some methods and facilities available for specific cases that can be done, but this reliability based, I would say a system reliability based method is a more first order, like you can say a lower fidelity than an FEM, but it is more relevant when we don't have a lot of data.
Okay. And then the second part of this was, did you account for bridge deterioration when generating the fragility surfaces?
Right. For fragility surfaces, the current fragilities actually do not account for deterioration, but the economic part does. So in future, that's something that we can look at.
Okay. Guy talked about slide 33, and could you elaborate on how the four components were integrated in your framework, particularly the observed NBI condition ratings and how they were integrated with the simulated condition deterioration models?
Right. So the PCA part of the analysis is just to check that the information that is provided by the four criteria is unique, or are there components that could be removed from this. And what we found from the PCA was that almost all of them are covering unique information. Even the fourth component covered more than 10% of the overall variance, which tells us that the four things that we actually listed cannot be reduced to 3. So that was the purpose of the PCA. When it comes to integration, we don't really integrate any of them together. As Eric presented in the final slide, prioritization is based on Pareto analysis, which is which of the solutions are non-dominated. So the bridge to be selected under priority needs to do well in, or needs to be non-dominated in all of these categories. So we don't use the PCA results directly to prioritize. The PCA result is a check to see whether we could try to reduce the dimensionality of our priority scheme.
Okay, I'm going to go ahead and turn it over to Don Digamon. We have a couple more questions left, and he can pick those up. Don?
Thanks, Paul. And you already beat me to the punch a couple of your questions. So anyway, question here. How is sea level rise addressed or considered?
Current formulation, we are using the hazard data as an input. We are not working on modeling the hazard itself. In this presentation, we use the 100-year flood scenarios that are available from FEMA. But if we want to include sea level rise, we would have to rely on other people's work on predicting the depth, flood depths and velocities that we can see. And our work would be downstream of that.
All right, very good. Another question, are you taking any consideration to the sufficiency rating from the CIDR? And I'm not sure what that acronym is. If the person who posted that question could place another statement in the question portal just to explain what CIDR is. But sufficiency rating, which is for bridge engineer, an older term that we don't use, but Nitesh, is that something that you can try to explain, or maybe you don't know what CIDR is either?
I say that we'll look into it, but I'm not currently aware.
And there was a question, how is scour susceptibility fit within this model? And if you can just talk about that again.
I think we answered that already. We are not developing scour susceptibility models, but how it's included is we are including the effect of it on the reduction in the axial and moment load carrying capacity of the foundation. So given the level of scour or the prediction of the scour for a bridge foundation, we'll need to adjust the calculation for what is the current capacity, axial and the moment load carrying capacity of the foundation. And that's how probability of failure under a given discharge through the bridge would be calculated in the form.
Okay, and there's clarity on the sufficiency rating, the CIDR. It is the Comprehensive Inventory Data Report. It's a biannual report received from FDOT to an agency for each bridge per NBI. So, Nitesh, does that give you some clarity, or still not something you're aware of?
There is I think they may be referring to a higher data quality than the NBI, and we are using it. We actually used it to develop some of the classification schemes that we used for the bridge fragilities. And this longitudinal data provides more information on the type of structure, as well as, say, the number of piers or the number of foundation piles and things like that, which were required in our initial development of the fragility. So we did include, or we used some of that data to do the fragility development.
All right, and we're getting close, so this should be the final question and statement. From your work, I see that you just picked Duval County. If you were to scale this up to, let's say, all the counties in Florida, just discuss real quick what the challenges would be with that.
One of the major challenges would be the availability of the input hydraulic models, because those are done at county level and they are very hard to obtain for the region in general. And that's something that we can try to work with other collaborators, and if we can do those in-house, that would be useful. The other thing would be looking at the inventory data and trying to figure out if we can get the best quality data for the inventory itself, because we had to do a lot of LiDAR based analysis at our end to figure out the exact elevations of different components, so that we could be sure about what is the flood depth and velocity that we would see at a site. These are few, but the next would be just the computational cost. It would be to replicate this for the whole state would be a big challenge when it comes to the amount of analysis that.
Well, thank you for those responses. So, Tord, I turn it back to you.
Thanks for very great presentation. The researchers at the FAMU, when this tool is available, maybe we can share it on your website, on our website. Like you said, it's going to be like a web-based tool that can be used by others. Maybe we can provide also the instructions that how they can collect the data for their estates, the area where they are interested to understand the potential damages to the bridge, or finding out which bridges are more important. So very, very interesting presentation. We thank you. I also would like to again reiterate that the deadline for submitting abstract for the 2026 conference is May 25, 2026, just around the corner. You can go to our website, or you can use the QR that you see to submit the abstract online. We are going to have the opportunity to see many of you who have enjoyed all our webinars, the monthly webinars, the research quarterly webinars, the in-depth webinars, and our other technology transfer activity and the research results. See you during the 2026 World Bridge Engineering Conference. On that note, we'll conclude our quarterly research webinar. And again, thanks for attending, and hope to see you in our next event.